choice for this worksheet, question 1. It says there the mass of the Earth is me, its radius is re, the magnitude of the gravitational field strength at the surface of the Earth is g, the universal gravitational constant is g. The ratio of g, small g over big G is equal to. Okay, so we have our formula for that G is equal to big G, mass of the Earth divided by the radius squared of the Earth, so R big E squared. So G over big G would equal ME over RE squared. So we would be looking at A. It's pretty straightforward. So looking at 2, which diagram best represents the electric field due to a negatively charged conducting sphere? Okay, negatively charged, it means that the direction that a positive charge would take would be attraction. So it would need to be into it. So it would be either one of these two, either C or D. But what happens, because it's a conducting sphere, all the charge, it generates itself equally inside. There's actually no electric field within. So it's actually going to be C. C would be your correct answer for that. Just going back to this over here, obviously for question 1, obviously we are using this for these two formulas over there for that. Here we have question 3. It says a point mass carries a positive charge plus Q and is at rest in a magnetic field. The field is in the direction as shown. The magnetic force acting on the charge is. Now, I just want to go to the formula that we would use. This is the formula here. Q V B sine of theta. Now, this would actually, obviously the force here is going to be 0. Now why? Because your velocity, the velocity is equal to 0 meters. It says that it's at rest. So it's going to be D. Question 4. The gravitational force between two unit masses separated by distance r is Fg, and the electric force between two unit charges separated by distance r is Fe. The Coulomb constant is K and the universal gravitation constant is G. The ratio of Fg to Fe is. Okay, so we're going to have Fg will obviously be G m1 m2 over r squared, and Fe will equal K Q1 Q2 over that same r squared. So we have that. So in looking at that, when we're looking at the ratio of Fg to Fe, we're obviously going to divide the one by the other. So when we divide, we invert in time. So we're going to get G m1 m2 over r squared, and we're going to be timesing by r squared K Q1 Q2. So these two will cancel, and we'll be left with G over K m1 m2 over q1 q2. Now looking here, we've actually got no answer that seems to be correct. Now the answer that was given correct was this one over here. So always give the best answer, because here we've got G over K, but obviously that just wouldn't be that. The size of the masses would, and the magnitude of the charge would also come into play, but this would be the best answer possible. All of these other ones definitely are incorrect. This one gets the G over K correct. So that sometimes happens in exams. Don't let that become a, just try and find, just choose the one that looks the best, closest to the best answer. Alright, here we have for question 5. We have a hollow metallic sphere is negatively charged. Which of the following correctly represents the electric field? We've just had this before, so this would be B. B is correct. That's for 5. That's just learning knowledge. Okay, question 6, it says, in the diagram, a long current carrying wire is normal to the plane of the paper. Normal 90 degrees to the plane of the paper. The current in the wire, and this is across, is directed into the plane of the paper. So we've got a current here, there's a cross there, it's going into the plane. Which of the arrows gives the direction of the magnetic field at point P? Now, remember, using the right hand, you put your thumb in the direction of the current, so your thumb would be pointing into the page, and your curled fingers give the direction of the magnetic field. So if I draw a circle like that, we would have like that. So it would be going in direction W. Great. Going on to next question, question 7. It says here, a small sphere X of mass m is placed at distance d from a point mass. The gravitational force on the sphere is 90. So we've got 90 is equal to g. We've got the mass placed next to a point mass. I'll call that small m, and it's a distance d, so that will be d squared. And then it says sphere X is removed and a second sphere of 4m. So now we have g, we have 4m, still the same point mass, but now we are looking that it's at a distance 3d, so it's going to be 3d squared. So we're going to get g 4m over 9d squared, which is equal to 4 over 9 gm over d squared. So we can see here that this is going to be 4/9. This over here is equal to that's equal to 90. So this is equal to 90, so it's 4/9 of 90, so the cancel that goes into 10 times, so it's going to be 14 newtons. So D is correct there. Going on to question 8. Which of the following diagrams illustrates the electric field pattern of a negatively charged sphere? Well, we've had so many of these. This one over here. Alright, so I think that's pretty straightforward. You should learn those. Going to question 9. We have a positively charged particle enters the space between two charge conducting spheres with a constant velocity directed parallel to the plate. So we've got this positively charged particle that's going in like that. It says the top plate is positively charged and the bottom plate is negatively charged. There is a magnetic field in the shaded region PQRS. The particle continues to move in a horizontal straight line, as I've drawn between the plates. Which of the following correctly describes the magnetic field direction? Well, if there was no magnetic field, what would happen because this is positive and this positive and positive repels positive, would get something like that. It would go down. So there must be a force that's this way, that's causing a force in that to balance that force. So you've got your force due to your electric field is in that way. We need a force due to the magnetic field in that way. We know that we've got our charge. It's a positive charge. It's in that direction. So our current is in that direction. So we using the right hand, we put our thumb in the direction of the current. We put our palm of our hand facing the direction of the force, and we see that our fingers are going into the board, into the plane of the paper. So it's going to be A. Looking at 10, it says the weight of an object of mass 1 kilogram at the surface of Mars is 4 newtons. The radius of Mars is about half the radius of the Earth. Which of the following is the best estimate for the ratio of the mass of Mars, mass of the Earth? Okay, so we've got for the Earth, if we take the Earth, now if it was 1 kilogram, the force on it would be about 9.8, let's say 10, it would be about 10 newtons, and that would be G, mass of the Earth, mass of the object, divided by the radius of the Earth squared. Now on Mars, it's 4, so it's 4 is equal to G. Now we got the mass of Mars, mass of the object is the same, and we see here that the radius of Mars is about half the radius of the Earth. So I'm going to about half the radius of the Earth all squared. So it says looking at the mass of Mars. So the mass of Mars then over the mass of the Earth. So the mass of Mars, if I do that there, is going to equal, now this will actually be a half, and you're going to square it, so it's going to be a quarter r squared. So we're going to cross multiply here, so we're going to get 4 times a quarter, so that's going to cancel out. We're going to get re squared divided by g, big G m, the mass of, and that's going to equal the mass of Mars. The mass of the Earth obviously would be 10 re squared divided by gm would be the mass of the Earth. So when we put these one over the other, I think you can see that the re squares are going to cancel, the g and the m are going to cancel, and you're going to be, because you're doing mass of Mars over mass of the Earth, we're going to get this 1 over 10 situation. So we're going to get a 0.1. Okay, so it's important to put it into your formula. Just put numbers in or symbols in and work from there. And here we've got 11 and 12. So we say it's here 3 positive point charges of equal magnitude are held at the corners x, y, and z of the right angle triangle. The point P is at the midpoint of xy. Which of the arrows shows the direction of the electric field at point P? Now, so we've got x, y, and z. Now, the electric field, because these are positive, it's going to be out. So C, this direction would be the electric field due to x. And this one over here would be the electric field due to y. And because they are going in opposite directions, because P is a midpoint and these are of the same magnitude, EX and EY will actually cancel each other out. And so you're just left with the electric field due to Z, and that's going to be out like that. That will be EZ like that. So it's going to be B would be your correct one there. And then finally, I think this is the last question for this. We've got here an electron traveling in the direction shown by the arrow X enters a region of uniform magnetic field. It leaves the region of the field in the direction shown by the arrow. So what happens here is that it does something like that. So obviously at this point, when it's at this point here, let's say it's at this point over here, just as it enters in, it's moving this way, so there's a force that's acting on in that direction. There's a force acting in that direction. Now, because this is an electron is going in this direction, we would say the current is going in the reverse direction. So we have got, if we take the right hand, we have our thumb in the direction of the current. We've got our palm of our hand facing up, so we need to turn our hand up, and so we'll have our fingers pointing out of the board. So it would be out of the plane of the paper. This would be the correct one there.